Hello and welcome to today's webcast titled Rapid Generator Degassing, Improving Personnel Safety in Power Plants. I'm Aaron Larson, Executive Editor of Power Magazine. I'll be hosting today's program, during which we'll hear from Steve Kilmartin. Steve is Director of Products and Markets for E1's Utility Systems business. He is an expert in the field of generator monitoring and maintenance and has authored numerous papers, including as Principal Investigator for an EPRI Maintenance Guide. Steve has been with E1 since 1988. He has also worked for GE and Mechanical Technology Incorporated in New York. The presentation is expected to last about 45 minutes and will be followed by a Q&A session. Before we get started, I'll run through a few housekeeping items. On the lower left-hand side of your screen, you should see an area where you can type and submit questions to the speakers. Feel free to send in questions at any time during the presentation, and we will try to answer as many as possible during the Q&A portion. Answers will also be sent via email to all attendees. If you are experiencing technical difficulty, you can ask for help by typing the problem in the same area on the lower left of your screen, and our production staff will assist you. Attendees can request a copy of the presentation by emailing Steve directly. His email address is skilmartin@e1.com and will be listed on the final slide of the presentation. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. Before we begin, I would like to thank E1 for underwriting today's program. The company's generosity allows everyone to attend the presentation at no cost. With that, I'll turn the program over to our speaker, Steve Kilmartin. Steve, take it away.
Thank you, Aaron. Rapid degassing or rapid purging of hydrogen-cooled generators is not a new concept. Several OEMs have been providing these systems for quite some time now. In most cases, the reason for rapid degassing is safety. However, they can also be used to save time during routine outages. During this webinar, we will cover challenges in today's power industry. We will review why we use hydrogen as a coolant gas. We will discuss safety concerns with hydrogen. We will discuss the components of a hydrogen cooling system. And we will go over the purging process. And then we will cover the requirements, considerations, and specifications of a rapid degassing system. Before I start, I would like to review some terms I will be using in today's webinar. I will use rapid or emergency interchangeably. I will also use purge, degas, and fill interchangeably. The difference between degas and depressurization is degassing or purging is replacing one gas in the generator with another gas. Depressurization is bringing the case pressure to 0 psi. These systems can be automatic, semi-automatic, or of course manual. These systems can incorporate solenoid valves or actuators to control the gas path. The control of these systems can be performed by the DCS or a PLC or in the hydrogen control cabinet itself. OEM stands for Original Equipment Manufacturer, such as General Electric, Siemens, Hitachi, Mitsubishi, and SOP stands for Standard Operating Procedure. The following are challenges today's power industry faces. The workforce is getting younger and leaner. The number of employees at power plants used to average at a coal plant in the neighborhood of 100 employees. Now they're in the neighborhood of 40 to 20 employees. Training programs are not what they used to be. A Apprentice programs used to be common in just about every power plant. The time between outages is getting longer. And why this is critical, or why this is important, is that when I first got into business, you would have an outage every year or every 18 months, maybe go every 2 years. Now outages are going out 10 years. And what this means is that you're not purging the generator as often, which means the employees that are purging the generator don't have the experience that they would have had 50 years ago when they would purge a generator every year. Generator fleets are getting older, as is the equipment that is, the auxiliary equipment that is attached on these generators. And OEM support is not what it used to be. You don't have as many people from General Electric, or in the old days Westinghouse, now Siemens. There's not as many to support you. Why do we use hydrogen? Hydrogen is a very relatively dense or relatively light gas. It has less windage and frictional losses. The relative density of hydrogen is 4 times less than air. What this means is that you can spin the rotor in a hydrogen environment a lot easier than you can if air is the cooling medium. This means you can generate more megawatts with less horsepower. Hydrogen has better heat transfer characteristics. It's 14 times more efficient at removing heat than air is. And with a generator, when you're generating electric power, you're creating heat. It becomes very important to be able to remove that heat from the components in the generator. The bottom line is more megawatts. You get more megawatts per pound of iron when you cool with hydrogen versus air. There are currently over 10,000 hydrogen-cooled generators in operation around the world today. There can be problems when dealing with hydrogen. Hydrogen, as we know, is very explosive. Hydrogen is colorless, odorless, and tasteless, which makes it very hard to detect if there is a hydrogen leak. And hydrogen is difficult to contain because the hydrogen molecule is so small. And then you also have an issue of the material compatibility. You have to make sure that the gaskets and metals that you're using with hydrogen are compatible to be used with hydrogen. As I mentioned in the earlier slide, generator fleets are getting older, as is the auxiliary equipment. And the workforce is getting younger and leaner, meaning less experience. And as I said, training programs aren't what they used to be, and the time between outages is getting longer. This is a headline from a local newspaper. I removed the name of the power plant. The death was a result of the purging process at this power plant. This explosion was a result of not knowing what gas was in the generator. Fortunately, there was no loss of lives in this explosion. Because of these issues, when using hydrogen, we've added another triangle to the fire triangle that includes using the proper equipment, having well-written and understood operating procedures or standard operating procedures, and having well-trained people. of the hydrogen. They're very thin, hard to see. There's yellow lines in there that show the hydrogen cooling path. The yellow circles on are the hydrogen seals between the generator case and the rotating field. Proper operation of these seals are critical, not only during normal operation, but during the purging of the generator. It is very important that the seals operate properly and the differential pressure between the hydrogen and the seal oil is correct.
Steve, I think we're having a little bit of trouble with your audio.
I've just gone to the headset. Is that better?
Yes, now it sounds good. Thanks.
Okay. Here's a sectioned view of a hydrogen seal. You can see that the seal oil comes into the seal on this particular seal at 95 psi, and that the hydrogen case pressure is at 90 psi. So what occurs is that the oil will flow not only towards the atmosphere or towards air, but it will also flow towards the hydrogen, creating a very effective seal in keeping hydrogen inside the generator. This is a typical hydrogen auxiliary system, P&ID. The circle on the right is the gas manifold, which is used to put gas in and take gas out of the generator, and used to maintain hydrogen pressure during normal operation. And the circle on the left is the generator gas analyzer. This is a picture of the hydrogen auxiliary skid, which contains the components that are called out in the P&ID of the previous slide. This generator gas, the generator gas analyzer is circled on the right, and the gas manifold is circled on the left. This is that P&ID again. You can see at the top where the CO2 supply pressure comes into the manifold. On the left-hand circle indicates a pressure of the CO2 supply, and it has a local indication, a pressure gauge, and it has a pressure transmitter which sends a signal back to the control room. These pressures become very important during the purging process. This is a picture of the CO2 Tank Farm on this particular system. This P&ID here shows the H2 supply going into the manifold. Again, we have a pressure indicator that is monitoring the H2 supply pressure for local indication, and we also have a pressure transmitter that is sending the 4 to 20 milliamp signal back to the control room. This is a picture of a hydrogen tank farm. The hydrogen can also be supplied from a bulk supply system or a hydrogen generator, which is seen in this picture. This is the air connection for the manifold on the P&ID. And this circle is showing a removable spool piece, which is used to minimize the chance of hydrogen and air being put in the generator at the same time. I use the word minimize because even with the spool piece, it is still possible to put hydrogen and air in the generator at the same time, which is to be avoided at any cost. This is a picture of that spool piece. This is a removable spool piece that can be either connected to the air supply or the hydrogen supply, but it cannot be connected to both. On this circle on the P&ID shows the hydrogen feed to the generator, the CO2 feed to the generator, and then there's a vent connection. And on the next slide, you can see where these connections from the auxiliary connect to the generator. And the CO2, carbon dioxide, will feed to a bottom distribution pipe or a bottom header. The hydrogen will feed to the hydrogen distribution pipe or the hydrogen header. CO2 being on the bottom because it's a heavier gas and you want to force the lighter hydrogen out the top, and hydrogen being a lighter gas, which you want to come in through the top to force the heavier CO2 out the bottom. When you're putting CO2 in the generator, the hydrogen line will act as a vent. The hydrogen distribution pipe will act as a vent or connect to the vent. And when you're putting hydrogen in, the carbon dioxide distribution pipe will serve as a vent. This circle on the P&ID is the gas analyzer portion of the skid. This picture is of the hydrogen skid, and it shows the portion that contains the analyzer. And this P&ID shows where the analyzer connects to the generator during normal operation. During normal operation, when the generator is spinning at full speed, the analyzer will connect to the generator fan pressure and the generator fan suction, which will create a flow through the analyzer. Another important slide, this is showing where the analyzer connects to the generator. And when I demonstrate the purging of the generator, it's going to be very important to note where the analyzer is connected. Now, at this point during normal operation, again, the analyzer is connected to the generator fan pressure and the generator fan suction. The analyzer is also piped to the gas manifold, the vent on the gas manifold. And this connection would be used during the purging of the generator. So again, it's important to note that the analyzer during normal operation is connected across the rotor, the generator fan suction and pressure, but during the purging process, it is connected to the manifold vent. So it's important that you change that whenever you go into a purge, especially when you're going into an emergency purge. And here, this is the connections where the connections would be made during the purging. As I mentioned earlier, the carbon dioxide distribution pipe will serve as either a feed or a vent, and the hydrogen distribution pipe will either serve as a feed or a vent. And we will connect the analyzer to the pipe which is being served as the vent. Now we're going to go over the purging process in the generator, and I hope that this works. The assumption here is that this generator has just been worked on and that it's got air in it. And the first thing that's going to take place is that we're going to pressure test the generator. So you see the air supply down in the bottom right-hand corner. We're going to remove the feed to this H2 supply, remove the feed to the CO2 supply, and connect the air supply. Don't look like this is working. So I'm going to have to walk through this slide. During the air pressure test, maybe it is working. During the air pressure test, we're connecting the air supply, and we're not putting air in the generator. We're actually just pressurizing the generator. So we got it connected. All the isolation valves are in the proper position, and now we're going to put air in the generator. Or maybe not. All right, again, I'm going to have to walk through this. So the air would, again, come into the generator. We'll fill the generator with air. We'll shut off all the isolation valves to the generator. By the way, this is working, but it's working very slow. And at that point, once we've passed the air pressure test, then we're going to put CO2 in the generator. So what we do at that point is we disconnect the air, and again, this is that removable spool piece. We disconnect the air, we'll connect the CO2 supply and the H2 supply, and we'll bring CO2 in the generator. CO2 being a heavier gas will come through the bottom header and will push the air that's in the generator out the top header. Now, if I had my analyzer connected to its normal position during normal operation, which are on the left-hand side, the analyzer feed and the analyzer return, as soon as I put CO2 in that generator, I'm going to have CO2 in the bottom of the generator, and those analyzers would see pure CO2. And so that would be a misreading since there's still air at the top of the generator. So where I want to take my purity reading during the purging of the generator is over on the right-hand side in the middle where it says Analyzer Purge Connection. It's in parallel with the vent so that as the gas is going out the generator, that's where we're measuring the purity. So as the heavier CO2 comes in the generator, the lighter air comes out the top header, out the vent, and we will not see CO2 until the generator is completely filled with CO2. And you just reverse that process for hydrogen when you're putting hydrogen in the machine. You'll put hydrogen in the top header. It being a very light gas will push the heavier CO2 out the bottom header. The bottom header will serve as a vent, and that's where our analyzer will be connected to monitor the purge gas during the purging process. Now, when we talk about rapid or automatic degassing, the critical components that we need to add here are solenoid valves, or you can use actuators. So we add a solenoid valve to the hydrogen supply. We add a solenoid valve to the carbon dioxide supply, and we add a solenoid valve to the vent line. And this will allow us to do everything that was done manually, we can now do automatically from a control room or for a control cabinet. To support the logic during this operation, during this rapid purge or automatic purging, you need additional information. And what you need is you need electrical signals from the case pressure that you need to know what the case pressure is. You need an electrical signal from the seal oil differential pressure. You have to make sure that your oil pressure, seal oil pressure, is higher than your hydrogen pressure so that you're maintaining that proper seal during the purging of the generator. You need to know what your H2 supply pressure is. You need to know what your CO2 supply pressure is. Also, with those gases, not only do you need to know what the pressure is, but you need to know the quantity on hand. And in some cases, power plants will actually weigh the CO2 to make sure that they have enough CO2 on hand to purge the generator. And then, as I mentioned earlier, you need to make sure that your gas analyzer is connected to the proper points on the generator or on the manifold, and you have to make sure that the analyzer is measuring the correct range. During normal operation, the analyzer will read H2 in air and should read in the neighborhood of 90 to 100%. When you're purging a generator, you're going to read CO2 in hydrogen, or you're going to read air in CO2. And these are ranges that need to be manually switched or manually changed. So if you are going from normal operation to an emergency or rapid degas, you need to make sure that your analyzer is reading the correct scale. The next 3 slides are really questions that need to be answered before you install a emergency or rapid degassing system. The first question is, how fast? How fast do you want to purge the generator? And in order to establish or calculate that, you need to know what the volume of hydrogen is in the generator case. You also need to know what the size of the piping is, the number of valves that are in the piping line, and what the orifice size of those valves are. You need to know the number of bends in the piping that goes from the skid to the generator, and you also need to know the length of piping. And all of that information you need to know before you can calculate how fast you can purge that generator. Then you have to ask yourself, do I want to do a blanketed purge, or do I want to flood the generator to purge it? One of them is a slower purge. A blanketed purge is slower. A flooded purge is much quicker, where you're just overwhelming the case with the gas that you want to put in the generator. And then again, and I've mentioned this several times, you want to make sure that your seal oil differential pressure is controlled and maintaining the proper pressure, oil pressure and hydrogen pressure. You need to determine what gas you are going to be using to purge the generator. You can use carbon dioxide, which I've used throughout this presentation and which is very common in the United States. You can use nitrogen, or you can use argon. With carbon dioxide, it's easier to maintain a blanket between the air in carbon dioxide and hydrogen and carbon dioxide. With nitrogen or argon, you're typically flooding the generator or overwhelming it with the gas that you want to put in it. If you are going to use CO2, there are 2 things that you should be very aware of, and one of them is the potential of pipe freezing. When you have a rapid flow of CO2, you could have the pipe freeze or valves freeze in the line. And you also have to be concerned about thermal shock, especially if you are doing an emergency purge where the generator is warm and then all of a sudden you're putting in a very cold CO2. You want to be aware of what thermal shock causes and what damage it could do to the generator. The control of a CO2 rapid purge or any rapid purge, it can be controlled by the DCS. It can be controlled by a programmable controller, or as I mentioned, it can be controlled by in the hydrogen skid itself. These purges can be either automatic or semi-automatic, or of course they can be manual. The difference between automatic and semi-automatic is that you would use the signals from your transmitter, your transmitters, your case pressure, your fan or your CO2 supply pressures, and your analyzer, and you would run a complete purge that's based on the logic of the signals coming in from these pieces of equipment. A semi-automatic is that a person would initiate the purge based on reading those instruments, knowing what the supply pressures of the CO2 and the hydrogen is, and what the analyzer is, what range it is set on. You can do a rapid purge or you can do a rapid depressurization. Both of them accomplish different things. You may just want to do a rapid depressurization to make sure that the case of the generator is no longer pressurized with hydrogen, minimizing the hydrogen leak out of the unit. In case you had for instance, in case you had a seal failure, you would want to do a rapid depressurization. A rapid purge will actually remove the hydrogen out of the generator and put CO2 in the generator, put in inert gas in the generator. And then you have to decide if you want to use solenoid valves as to control the gas flow, or if you would want to use actuators to control the flow. The solenoid valves come in various configurations, which you can actually be electrically controlled, air controlled, and I believe some of them even have an override, a manual override. An actuator typically is electrically controlled, and the nice thing about actuators is that you can override them if you lose power and you need to. Here are considerations, and we've discussed these, but you need to know that your analyzer is connected to the correct point on the generator when you're doing your purge. You don't want to be connected where you connect during normal operation. You want to be connected to the vent where the gas is venting the generator. And you want to make sure that that analyzer is set to read the right combination, whether it's air and hydrogen, CO2 and hydrogen, or air and CO2. Your case pressure, you not only want to have a indication, local indication to tell what your case pressure is, but you also want to have a signal that feeds back to the control room so that the control room knows what the case pressure is. And that is the same with the hydrogen supply and the CO2 supply. It's good to have local indications because these units are normally, the hydrogen supply and CO2 supply are normally under the belly of the generator. You want to have a local indication for operators or INC to be able to view that down where the tanks are. And you also would like to have a 4 to 20 milliamp signal that goes to the control room so the operators know what the supply pressures are. One thing to note that the variation in design in the fleet, you can actually have two sister generators, and the design of the hydrogen auxiliary system could be slightly different. So you want to be aware that just because, for instance, you have a GE Frame 7 system, not all of the hydrogen auxiliary systems connected to them are the same design, so that when you're looking to incorporate a rapid system or a auto purge or emergency purge system, you're going to need to review each design individually. You want all of your equipment that is used to be rated to be used in a hazardous area. Anything that's electrical, such as solenoid valves, actuators, your purity analyzer itself, all of the equipment that's used in where there's hydrogen, needs to be certified or rated to be used in that area, which is a hazardous location. The hazardous locations will vary depending on country, or the certification will vary depending on country. In the United States, it's NEC, North American Electric Code. In Europe, it's either ATEX or IECEX. And then when you incorporate a rapid purge system, you need to change your standard operating procedure and your operating philosophy. They need to be modified to incorporate the emergency purging or rapid purging system. In summary, we know hydrogen is an excellent cooling medium. We also know the purging process is a critical operation, and there are safety concerns you need to be aware of. We reviewed the different components of a hydrogen auxiliary system and what takes place during the purging process. We ended by discussing the requirements and considerations that need to be addressed before incorporating a rapid degassing system. Remember, it's all about safe and efficient operation. Now for a little advertisement. If you found this webinar to be valuable, you may be interested in a generator auxiliary system symposium that GE conducts E1 conducts on a semi-annual basis. And we are having one this year. And if you would like more information or learn more about generator auxiliary systems, this is a pretty good symposium. We are having one later this year, and if you contact E1, you can get more information on this symposium. Thank you.
All right. Thank you, Steve. That was a great presentation, very informative and interesting. And we've had a number of questions that came in during while you were speaking, and we're going to try to consolidate similar questions and answer as many as possible in the time that remains. Any questions that we are not able to answer due to time constraints will be answered via email after the program. So, to get things started, where would you recommend installing a manual or automatic degas pull switch, or manual and automatic degas pull switches?
The ideal location is in the control room. They've got more information. They got all the information in the control room, so you would want to have them to have control, because there are issues that you certainly don't want to do a rapid or emergency purge while the generator's online. So you want to make sure the generator's offline. You want to make sure that the speed of the generator is low and you're not connected to the grid before you initiate any type of purge, whatever the purge might be. So the only place that you really have that information and the people that are qualified to initiate that are the operators in the power plant. So it should be in the control room.
Okay. Is the CO2 fill completed at atmospheric case pressure?
Say that one more time.
When you fill the carbon dioxide in, do you do that at atmospheric case pressure? This will vary between OEMs, but it doesn't vary that much. Typically what you will do is that, and I'll use the example that hydrogen is in the machine. What you would do during the purging process is the first thing you would do is shut off the hydrogen supply, and then you would open the case to vent through the CO2 header, and that will bring it down to around atmosphere. I think what they normally do is they want to be down around 4 psi, 5 or 4 psi, before they'll begin to put the CO2 in. So let's say they get it down below 4 psi, then what they're going to do is bring in the CO2. So they shut the vent, they shut that CO2 which was being used for the vent. They're shutting that off, opening at this point they don't open anything. They put CO2 in the generator, and they bring CO2 in at, and again, this would depend on the OEM, but they would bring the CO2 pressure to about 10 psi, and then they'll open the hydrogen to vent, the hydrogen header to vent, so that now the CO2 is coming in at about 10 psi, forcing the hydrogen out the vent. Okay, I think that answers the question. Are there various codes or standards or OEM requirements that require or recommend rapid degas systems?
As I mentioned earlier in the presentation, I know one particular OEM that supplied rapid degas systems as a standard component of their generators. Now, the reason that they did this is that they initially thought that some of these combined cycle plants could be unmanned or be manned, have limited manpower. So they wanted to be able to, if there was any type of condition that would generate or should generate a purge, these systems had it automatically designed into it. I would not be able to make that type of recommendation. That would be obviously an OEM generator manufacturer that would have to make that type of recommendation.
Okay. Now this next question has actually multiple parts, so I'm going to kind of go through them one by one. If you have a hydrogen leak during normal operation, where are the major leaks or losses of hydrogen likely to occur?
Okay. As I mentioned, one of the more difficult places to seal the hydrogen, but is also very effective, is the hydrogen seal itself. So the seal that is on the rotor, and on the collector end of the rotor and the exciter end of the rotor, that's a critical area and a difficult place to seal, but it's done very well with the hydrogen seals. Places where you might otherwise get leaks is through the bushings in the bottom or top of the generator. Bushings can break down and you can have leaks through the bushings. Obviously, any point that penetrates the generator case, any piping, the hydrogen supply feed, the CO2 supply feed, the connections going to the analyzer. If you have a hydrogen dryer, there's a point for leaks. If you have a hydrogen or a generator condition monitor, they could be a point for leaks. So any piping or instrumentation that is connected to the generator, there are also points where leaks can occur. Oh, and also liquid level detectors. Most generators will have at least one. A lot of them have 3 or 4 liquid level detectors, and these are also a point where leaks can occur. And by the way, plants, I recommend that plants have a procedure. Should they note that they're using a lot of hydrogen, if their normal usage is 300 cubic feet per day and that goes up to 600 cubic feet per day, they should have a procedure or process to identify that leak. And if they don't, they probably should get in touch with another power plant which does have, and they use it, copy it. Power plants usually are pretty good at sharing information.
Okay, and that actually leads right into another part of this same question. What is a typical hydrogen consumption for a given generator size? Is there a typical number that you could kind of throw out there that would mean everything is still okay?
Again, it depends on the generator itself, depends on the style of the generator. It depends on, for instance, one manufacturer has a seal oil system that is called a scavenging seal oil system or a bleed and feed seal oil system. And on those systems, you're using hydrogen. It's just the nature of how the piece of equipment works. Those units will use a little bit more hydrogen than what a system that's got a vacuum treated seal oil system. But the leakage or usage of hydrogen can vary. I would say anywhere from 500 cubic feet to 1,000 cubic feet per day. If you go over 1,000 cubic feet, that might be an indication that you got a problem. But you have to consult with the OEM to see what their recommendation is.
Okay, and if in that case, how do you address safety around leaks? How should safety be handled around leaks?
You have to be very careful. The one thing that you got to be very concerned about is where hydrogen can accumulate, because it is very light, it goes up. So if, for instance, you have a leak in your bushing box, which is located underneath the generator, where that hydrogen can travel when it goes out of that bushing box. If it, for instance, can just wrap around the generator, and this is an outdoor generator, and it just goes up, you don't have to be as concerned. Obviously, you got to be concerned about a hydrogen leak, but not as concerned. If you have some cabinet down there or some skirting on the generator that might be trapping the hydrogen, now you got to be concerned. Because that now you got a potential for an explosion. If you've got an indoor unit and you've got a bad leak, and the hydrogen is going to go up into the turbine deck, and if there's no venting, there's a potential that that hydrogen can accumulate up at the top of the turbine deck. Now, I've never heard of this happening, but I guess there's a potential that it could. You mainly need to be concerned about the areas skirting around a generator, around a bushing box, in a hydrogen cabinet, a collector cab. You have to be concerned where hydrogen can accumulate. I always recommend that in Environment One's field service people all have portable hydrogen leak detectors that they carry with them at all times when they're working in power plants. They also have a hydrogen sniffer so that when they're working on equipment, they can sniff for hydrogen leaks before they begin working on that equipment and verify that there is no leaks in the area that they're working.
Okay. And the next question is, are there any benefits to the slower purging process?
Yes. Well, there's pros and cons. The one benefit is they say this actually can be debated, but they say that you will use less gas to purge if you're going to do a blanketed purge. If you're going to maintain that blanket between the CO2 and hydrogen, that you will use less CO2. Now, there are companies that will state that that's not true, that even if you do a flooded purge where you're overwhelming the case with the purge gas, that you'll use about the same amount if you did a blanketed purge. Now, when you're filling the generator with CO2 or hydrogen, I think you always want to maintain that blanket, because you don't want the hydrogen mixing with the CO2. You want to make sure that you got pure hydrogen in there. So doing any of the other purging or degassing or filling with the inert gas is fine. When you're putting hydrogen in the machine, you want to maintain that blanket.
Okay. This is related to hydrogen analyzers. And do the E1 hydrogen analyzers have ability to remote mode switching, H2 to air and CO2 to air? Or CO2
Our standard piece of equipment does not. However, we have modified units for utilities that will allow them to switch what concentration of gas is being measured, and also will change the output range, because when you're in a normal mode of operation, the range of our analyzer is 80 to 100 or 70 to 100. When you're in the purge mode, you want to go 0 to 100. So you want to change the scale, and you want to change the gas concentration mixture or range. And we have supplied equipment that will do that.
Okay. I think you kind of touched on this during your presentation, but how is thermal shock and line freezing controlled in rapid degassing systems?
With a CO2 vaporizer or CO2 heater. So what you're doing is between the tank farm and the generator, you're putting what is called either a vaporizer or a heater in line with the CO2, so that you're heating that CO2 before it goes into the generator. So that's the way you control that thermal shock or control the temperature of the CO2.
All right, this one is a little bit off topic, but it says, during your presentation, I saw you reference a hydrogen generating module. How common is this? Is there a size of unit that it makes economical sense?
There are different sizes. They seem to be a popular product in countries where hydrogen is not readily available or hydrogen is difficult to transport. I can tell you that there's plants most of the plants, for instance, in South Africa, have hydrogen generators on them. They actually use both. They'll have tanks as backup, but most of their hydrogen comes from the hydrogen generator. It seems to if you talk to the hydrogen generator company, they can calculate the feedback or payback on using those devices. In the United States, I don't know what that is, but I know in other countries there is a benefit in using those hydrogen generators.
Okay. Does all carbon steel vent piping need to be changed out to stainless, and should any other carbon steel piping be converted to stainless?
Environment One uses stainless on all of their products, but I would venture, and this would be a guess, that most of the hydrogen systems in the United States are carbon steel. Would I recommend using stainless steel? Yes, I would recommend using stainless steel. I would not, however, recommend replacing carbon steel just to change to stainless steel. I would change from carbon steel if there's restriction in the piping, or it's contaminated, or it's not in good shape. As far as the vent pipe, the main concern with a vent pipe is you want to make sure that it's grounded, so that if you got a carbon steel or even a stainless steel that has a coating on the inside of it that will not allow it to be vented, hydrogen can build up a static charge. Clean, dry hydrogen can build up a static charge. And when that static charge builds up, it can cause an arc or spark, which can cause a fire. And not that it's common, but there have been fires in vent pipes. So the material, although stainless steel is better than carbon steel, however, the critical thing in a vent line is making sure that that vent line is grounded.
All right, next question. Does rapid purging result in erroneous hydrogen readings due to mixing of the gases?
Yes, or can. You want to make sure, first of all, again, you're taking your sample out of you're going to take your purity reading out of the vent line. If you, as an example, if you do a blanketed purge and you're reading air coming out of your vent line, as I mentioned, and CO2 coming into the bottom header, that vent line will read air until all of the air is out of the generator and CO2 has reached the top. If you do a rapid purge, now you've got air and CO2 mixing, so that your CO2 purity reading immediately will come down, so that you need to be more aware of when that reading is down into the lower level, and be a little more conscious of that. If it says that it's 10%, well, you might want to let that run for just a little longer than normal to make sure that it stays at 10%. It still doesn't keep dropping. There is mixture that takes place, and that you have to be more aware of your purity reading if you're going to do a rapid purge. More conscious of it.
All right. We're coming up on the top of the hour, but I think we've got a quick one here, and then we'll probably have to wrap it up and answer the rest via email. Will the gas monitor work if using nitrogen?
Yeah, no. This is what has taken place in Europe is they're starting to use nitrogen as a purge gas instead of CO2. The problem with our analyzer in measuring nitrogen is that nitrogen's thermoconductivity is very close to air. So it's difficult to distinguish between air and nitrogen. So you can use our analyzer for hydrogen purity. You could use our analyzer to measure CO2 in hydrogen, but when you go from, or it would be nitrogen, but when you go from nitrogen to air, you need to use an oxygen sensor in conjunction with our piece of equipment to be able to deviate or tell the difference between nitrogen and air. Just as a note, Environment One is currently working on a system that which will incorporate 2 sensors, a thermal conductivity sensor and an oxygen sensor, that will allow you to measure any kind of purge gas, whether it be CO2, argon, or nitrogen.
All right. Well, thank you, Steve. Great job with the presentation and answering the questions. And as we said, we will address further questions individually via email, and all attendees will receive answers to the questions. Thanks once again to E1 for underwriting today's event, and thank you all for attending. We hope you found today's presentation beneficial and that you have a great day.
Thank you.